What if you could send a message to your past self? Not a memory, not a regret, but a real, physical note, slipped into your own hand on the morning of your 10th birthday, or whispered into your ear the moment before you made that one decision that changed everything. It's a thought that feels like pure fantasy, the stuff of dreams and science fiction blockbusters. But what if the laws of physics, the very rules that govern our universe, don't explicitly forbid it? This isn't just a whimsical idea. It's a genuine question that emerges from one of the most mind-bending concepts in theoretical physics: closed time-like curves, or CTC. These are not machines or portals, but theoretical pathways woven into the fabric of spacetime itself, potential loops that could, according to some solutions to Einstein's equations, allow for travel into the past. We're about to embark on a journey to the very edge of known science, to explore a possibility that challenges our most fundamental understanding of cause and effect, of memory and destiny. Think about the stories that have captured our imaginations for generations. The Doctor's erratic travels in the TARDIS, Marty McFly racing through time in a DeLorean, the intricate plots of films like Tenet or Interstellar. These narratives resonate so deeply because they tap into a universal human longing, the desire to revisit, to correct, to understand. Closed time-like curves take that longing out of the realm of fiction and place it squarely on the chalkboards of physicists. They represent a frontier where our everyday logic begins to break down, where the sequence of events we take for granted could, in theory, coil back on itself. This video is an invitation to explore that frontier with a sense of wonder and scientific curiosity, to see how the universe might permit such incredible journeys. We'll begin our exploration at the source with the revolutionary ideas of Albert Einstein, whose theory of general relativity first opened the door to these bizarre possibilities. From there, we'll navigate the strange and violent cosmic environments where CTCs might exist, from the dizzying depths of rotating black holes to the theoretical constructs of wormholes. But the journey doesn't end with the math. The existence of closed time-like curves forces us to confront profound philosophical puzzles, the infamous grandfather paradox, where you might prevent your own existence, and the deeper questions about free will and a predetermined universe. This is more than a lecture. It's a detective story, piecing together clues from the cosmos to answer one of humanity's oldest and most captivating questions. So get ready to stretch your imagination, because we are diving deep into the science, the speculation, and the stunning implications of looping back to our own past. To truly grasp this idea, we first need to step away from the complex math and return to a simpler concept, our everyday experience of time. We think of time as a straight line, an arrow flying from the past through the present and into the future. We move along this line in one direction only. Now, let's introduce Einstein's revolutionary insight. His theory of general relativity tells us that space and time are not separate stages, but are woven together into a single, dynamic fabric called spacetime. Massive objects like stars and planets warp and curve this spacetime fabric, and what we perceive as gravity is actually the effect of objects following the curves in this fabric. This is where the concept of a worldline becomes essential. Imagine your entire life not as a series of moments, but as a single, unbroken thread stretching through the four-dimensional tapestry of spacetime. This thread, your worldline, marks your path from birth to the present moment and beyond. Normally, this thread always points toward your future. Now, the term timelike is the crucial piece. A path through spacetime is called timelike if it represents a trajectory that any material object, like a person or a spaceship, could realistically follow without breaking the cosmic speed limit, the speed of light. It's a path where motion through time is dominant. So, what happens when this thread, this timelike worldline, doesn't just extend forward but actually bends in such an extreme way that it loops back and connects to its own past? That is the essence of a closed time-like curve. It's a path through the universe where, if you were to follow it, you would eventually return to the exact same event in space-time from which you began. You would meet your past self. A helpful analogy is to think of drawing a circle on a flat piece of paper. An ant starting at one point on the circle can walk all the way around and return to its starting point in space. Now imagine that circle isn't drawn on a flat surface, but is instead a path carved into the very fabric of space-time itself, where one of the dimensions is time. The ant would return to its starting point in both space and time. It's vital to distinguish closed time-like curves from other popular time travel ideas. They are not a machine you build like a DeLorean with a flux capacitor. They are not a mystical portal that appears out of nowhere. Instead, CTCs are proposed as natural, albeit highly exotic, features of the universe-specific solutions to Einstein's field equations. They are not a violation of the rules, they are a bizarre consequence of the rules when pushed to their absolute limit. This is what makes them so compelling to physicists. They aren't magic, they are an extreme prediction of our most successful theory of gravity, suggesting that the universe might, under the most extreme conditions, allow for the past and future to touch. But before we can explore these cosmic loops, we have to understand the engine that makes them possible. That engine is Einstein's theory of relativity, a two-part revolution that completely reshaped our understanding of space, time, and gravity. It all began in 1905 with special relativity. Before Einstein, scientists like Newton thought of space and time as absolute and separate. Space was a fixed three-dimensional stage, and time was a universal clock ticking away at the same rate for everyone, everywhere. Einstein shattered that idea. He proposed that space and time are relative. They depend on your frame of reference, specifically how fast you are moving. He united them into a single, four-dimensional continuum called spacetime. This was a monumental shift. Think of it like this. You can describe your location in a city by its street address, which is like space and the time of day. Special relativity said that these two pieces of information are fundamentally linked. Your where and your when are just different aspects of your position in the unified fabric of spacetime. One of the most famous and bizarre consequences of special relativity is time dilation. Einstein showed that the faster you move through space, the slower you move through time. If you were to embark on a journey on a spaceship traveling at a significant fraction of the speed of light, time for you would pass more slowly than for someone who remained on Earth. Upon your return, you might have aged only a few years, while decades or even centuries had passed for everyone back home. This isn't just a theory. It's been experimentally verified with incredibly precise atomic clocks on fast-moving airplanes. Special relativity gave us the first hint that time is not the rigid, universal constant we perceive it to be. It's flexible, it's personal. It set the stage, but it was general relativity, completed a decade later in 1915, that truly opened the door to the possibility of time loops. General relativity took the concept of unified spacetime and added a dynamic, geometric layer, gravity. Einstein proposed that what we feel as gravity is not a mysterious force pulling objects together, but rather a consequence of the curvature of spacetime itself. Mass and energy tell spacetime how to curve, and curved spacetime tells objects how to move. A common and helpful visual is to imagine spacetime as a vast, taut rubber sheet. If you place a heavy bowling ball in the center, it creates a deep dimple. Now roll a marble near this dimple. The marble won't travel in a straight line. It will curve inward, orbiting the bowling ball as if attracted to it. The marble is simply following the curved geometry of the sheet. In our universe, the sun is the bowling ball, and the Earth is the marble, seamlessly following the curvature of spacetime created by the sun's mass. This curvature is the key ingredient for closed time-like curves. In most situations, like our solar system, this curvature is gentle. the paths objects follow, their world lines, remain open, they stretch forward in time without looping back. But general relativity allows for solutions where the curvature is so extreme, so violent, that the fabric of spacetime is twisted into incredibly complex shapes. Around infinitely dense objects or in the presence of massive rotational energy, the equations suggest that these world lines could be bent so severely that they fold back on themselves. The time-like path of an object could curve around so sharply that it connects to a point in its own past, creating a closed loop. It's as if the gentle, sloping valley in our rubber sheet analogy contorts into a whirlpool or a knot where a path exists that circles back to its own beginning. This isn't a flaw in the math, it's a feature of a universe where spacetime is a dynamic, malleable entity. So, if general relativity allows for these spacetime contortions, where do we actually find them? The first serious, mathematically rigorous example didn't emerge from a blackboard in a physics department, but rather from the mind of one of the 20th century's greatest logicians, Gödel. Best known for his incompleteness theorems, which fundamentally reshaped our understanding of mathematics itself, Gödel decided to turn his formidable intellect to Einstein's equations. In 1949, as a colleague and close friend of Einstein at the Institute for Advanced Study in Princeton, he presented a birthday gift to the great physicist that was as unsettling as it was brilliant, a new solution to the equations of general relativity that allowed for time travel. Gödel's model was not based on black holes or wormholes, but on an entirely different concept, the universe as a whole. He proposed a universe that was not expanding as ours is, but one that was uniformly filled with a slowly rotating, pressurized fluid. Think of it as a vast cosmic soup that is gently spinning. This overall rotation or vorticity is the crucial ingredient. In our everyday experience, we don't feel the universe spinning around us, but Gödel's model showed that if the entire cosmos had even a very slight rotation, it would impart a profound twist to the fabric of spacetime on the largest scales. This twist wouldn't just affect the motion of galaxies, it would alter the very nature of time within the universe. In this rotating Gödel universe, the paths that objects can take through spacetime are no longer simple, forward-moving lines. The global rotation creates what physicists call frame dragging, an effect where spacetime itself is pulled around by a rotating mass. We see a mild version of this around rotating planets like Earth, but in Gödel's model, the effect is universal and cumulative. As a result, the timeline, the direction that defines the future, begins to spiral. Gödel showed that in such a cosmos, an astronaut with a sufficiently powerful rocket ship could embark on a journey. They wouldn't be traveling faster than light or diving into a singularity. Instead, they would follow a wide, spiraling path through this rotating universe, a path that Gödel called a closed time-like curve. By navigating this immense cosmic corkscrew, the astronaut could eventually loop back, not just to their starting point in space, but to an earlier point in time. They could, in theory, arrive back at their launch pad before they ever took off. The implications of this were staggering, and Einstein was reportedly deeply troubled by them. Gödel had not found a loophole or a crack in general relativity. He had found a valid, self-consistent solution that emerged directly from Einstein's own equations. It demonstrated that time travel wasn't necessarily a logical absurdity that could be dismissed out of hand. It was a genuine mathematical possibility within the framework of the theory. This forced a profound philosophical confrontation. If the laws of physics allow for journeys into the past, what does that mean for our understanding of cause and effect? Does it imply that the past, present, and future all exist in a static, predetermined block, much like the frames of a film reel? Gödel himself leaned toward this block universe view, suggesting that the distinction between past and future might be an illusion, a peculiarity of our particular perspective within a more complex cosmic structure. While we now have strong evidence that our actual universe is expanding and not rotating in the way Kerr described, his model remains monumentally important. It was the first concrete proof that closed time-like curves were not just science fiction, but a subject worthy of serious scientific inquiry. It pulled the concept from the fringes and placed it squarely on the table for physicists to wrestle with, setting the stage for the even more extreme environments where we continue to hunt for these temporal loops today. While Gödel's universe was a fascinating theoretical playground, the quest for practical time travel naturally leads us to a more compelling and visually striking concept, the wormhole. Often depicted in science fiction as a shimmering tunnel or a cosmic shortcut, the wormhole, or Einstein-Rosen bridge, is another legitimate solution to the equations of general relativity. Imagine the fabric of spacetime as a vast, flat sheet of paper. To get from a point on the left side to a point on the right, you would normally have to travel the long distance across the entire surface. But what if you could bend the paper so those 2 points touch, and then punch a hole through the contact point, creating a direct tunnel? That's the essence of a wormhole, a bridge connecting 2 distant regions of spacetime through a shortcut in the higher dimensional fabric of the universe. A natural wormhole, as predicted by the math, would likely be incredibly unstable, collapsing into a singularity in an instant, far too quickly for anything to pass through. However, physicists like Kip Thorne and his colleagues explored the idea of a traversable wormhole, one that could be kept open long enough for matter, or perhaps a spacecraft, to journey through. This would require the presence of a truly exotic form of matter with negative energy density, something that pushes spacetime apart rather than pulling it together, acting as a kind of cosmic scaffolding to prop the tunnel open. While we have no evidence such exotic matter exists in sufficient quantities, the theoretical possibility allows us to play out a truly incredible thought experiment: how to turn this spatial shortcut into a machine for traveling through time. The transformation begins with a simple, stable wormhole. Let's picture it clearly. It has 2 mouths in 2 different locations. For the sake of our story, let's place mouth A here on Earth and mouth B on a distant spaceship. Initially, these 2 mouths are synchronized in time. If you look through mouth A, you see the interior of the spaceship at the present moment, and an astronaut looking through mouth B sees Earth at the very same moment. They share a common now. The magic happens when we put the principle of time dilation from special relativity to work. We send the spaceship carrying mouth B on a journey at a significant fraction of the speed of light. As we know, time for the moving mouth will pass more slowly compared to the stationary mouth back on Earth. Let's say the spaceship journeys for 10 years of its own time. Due to time dilation, 50 years pass on Earth. When the spaceship returns and parks next to mouth A, we have a profound situation. Mouth B, having been on the fast-moving journey, is now 10 years older than when it left. But mouth A, which stayed on Earth, is 50 years older. This creates a fixed time difference between the 2 ends of the tunnel. If you were to step into mouth on Earth in the year 2074, you would exit from mouth B into the spaceship, which exists in its own reference point only 10 years after it originally left, let's say the year 2034. You have traveled 40 years into the past. Conversely, stepping into mouth B on the spaceship would send you 40 years into the future of Earth. The wormhole is no longer just a bridge through space. It has become a gateway through time. Each passage through this engineered wormhole would itself be a segment of a closed time-like curve. Your world line, from stepping into the future dated mouth to emerging from the past dated mouth, would form a loop in spacetime, connecting a later event to an earlier one. This elegant theoretical model demonstrates with stunning clarity how the laws of physics, as we currently understand them, might permit the construction of a time machine without ever requiring faster-than-light travel or defying relativity. It simply requires harnessing 2 of relativity's own most astonishing effects: the spatial curvature that allows for wormholes and the time-warping effects of high-speed travel. While the engineering challenges are, to put it mildly, astronomical, the underlying physics suggests that the universe might not have a fundamental rule against visiting yesterday. But what if a traversable wormhole proves too fantastical an engineering feat, even for a hyper-advanced civilization? Are there other, perhaps more naturally occurring, pathways through time hidden in the cosmos? This leads us to one of the most exotic and speculative ideas in all of theoretical physics: cosmic strings. These aren't the vibrating strands of superstring theory. Think of them instead as cosmic fossils, unimaginably thin cracks in the fabric of the universe left over from the first moments after the Big Bang. In that primordial, searingly hot state, the universe underwent a series of phase transitions, much like water freezing into ice. And just as ice crystals can form with cracks and imperfections, space-time itself may have crystallized with flaws, one-dimensional defects of pure energy. A cosmic string would be a thread of inconceivable density, thinner than a proton but with the mass of a mountain range crammed into every centimeter. A single string stretching across the observable universe would warp the space around it so severely that it would act as a gravitational lens, bending the light from galaxies behind it. The connection to time travel was first rigorously explored by physicist J. Richard Gott in the 1990s. He realized that the sheer mass energy of these strings creates an intense gravitational field, and general relativity tells us that any mass in motion drags spacetime along with it, an effect known as frame dragging. Now imagine a single cosmic string. Its gravitational influence is powerful, but the spacetime around it, while curved, doesn't necessarily form a time loop. The magic happens when you have two of these strings. Picture two infinitely long, incredibly dense cosmic threads moving past each other at a velocity approaching the speed of light. As they pass, their combined, rapidly moving gravitational fields would twist the spacetime between them into an incredible configuration. Gott showed that this specific setup could create a region where timelines are bent into a closed curve. It's a bit like two incredibly fast ice skaters spinning on a rink. If they pass close enough to each other, the whirlpool of spacetime they create in their wake could, in theory, loop back on itself. An object traveling on just the right path through this warped region could find its future pointing directly toward its past. What makes this idea so compelling and yet so challenging is that it relies solely on the well-established principles of general relativity, without requiring any speculative exotic matter to hold a tunnel open. The time machine is built from the geometry of spacetime itself, twisted by the raw gravitational power of these primordial relics. This positions the search for cosmic strings as one of the most thrilling frontiers in cosmology. Astronomers are actively looking for their signatures, scanning the sky for the telltale double images of distant galaxies caused by a string's gravitational lensing, or for unique ripples in the cosmic microwave background radiation, the afterglow of the Big Bang. Finding evidence of cosmic strings would not only provide a direct window into the universe's earliest moments, it would also tell us that the ingredients for closed time-like curves might be woven into the very structure of our cosmos, having existed since the beginning of time, waiting to be discovered. Now, with all these theoretical pathways laid out before us, from whirling universes to cosmic strings, we arrive at the unavoidable question, the elephant in the room that every discussion of time travel must eventually address. If you truly could step into a closed time-like curve and journey to a moment before you were born, what would stop you from disrupting the very chain of events that led to your existence? This is the grandfather paradox, the most famous and visceral thought experiment against the possibility of backward time travel. Imagine traveling back to the 1920s, finding your grandfather as a young man, and somehow preventing him from ever meeting your grandmother. If you succeed, then your parent would never be born, and consequently, you would never be born. But if you were never born, then who traveled back in time to interfere in the first place? The entire scenario creates a logical contradiction, a loop of cause and effect that seems to unravel itself. This paradox strikes at the heart of our everyday understanding of reality. We live in a world where causes come before effects. A ball breaks a window because it was thrown first. You exist because your ancestors met and had children. The grandfather paradox suggests that time travel could shatter this fundamental principle, allowing an effect, your own existence, to reach back and eliminate its own cause. It presents a universe that would be inherently inconsistent, a place where history could be rewritten in a way that creates impossible, self-canceling situations. For many, this logical inconsistency is the ultimate proof that time travel must be impossible, a built-in safety mechanism within the cosmos that prevents such chaos. Yet, physicists and philosophers have proposed several compelling ways the universe might resolve this conundrum without outright banning time travel. One of the most straightforward solutions is the idea of a single, immutable timeline. In this view, the past is fixed and unchangeable. You might travel back in time, but any attempt to alter a key event would inevitably fail. Perhaps your gun would jam, or you would get caught in traffic, or a sudden change of heart would stop you at the crucial moment. The universe, in this scenario, acts as a cosmic editor, ensuring that events unfold exactly as they always have. Your journey to the past was always a part of history. You were always there, a witness or perhaps even a minor participant, but never an agent of fundamental change. This preserves consistency but raises profound questions about free will. Are our choices truly our own, or are we just actors performing a script written across spacetime? A more nuanced version of this is the Novikov self-consistency principle, proposed by Russian physicist Igor Novikov. This principle actively asserts that any actions taken by a time traveler were always part of the timeline. There is only one history, and it is entirely self-consistent. The paradox simply cannot arise because the laws of physics will conspire to prevent it. For instance, if you go back with the intention of stopping your grandparents' meeting, you might accidentally be the very reason they are brought together. Maybe you cause a commotion that pushes them into each other's arms, or you deliver a message you thought was unimportant that ends up being the catalyst for their romance. In this view, closed time-like curves don't create alternate realities. They simply enforce a single, seamless loop where every action fits perfectly into a pre-existing pattern. But what if the universe isn't so rigid? Another popular resolution, heavily favored by science fiction, is the concept of branching timelines or the multiverse. In this model, the moment you arrive in the past, you create a new, parallel universe that diverges from the original. In this new branch, you might successfully prevent your grandparents from meeting. You would then exist in that timeline as a paradox from another world, but your own original timeline remains untouched, a separate reality where your history is preserved. This elegantly sidesteps the logical contradiction. Your actions don't erase your own past, they simply spawn a new future. However, this solution comes with its own philosophical weight. It suggests an infinite number of realities branching from every decision, a cosmos of endless possibilities where every what-if is played out in some other universe. While this is a thrilling concept, it removes the emotional stakes of changing your past. You're not fixing your own history, you're merely becoming a refugee in a new one. Each of these resolutions offers a different lens through which to view causality and our place in the cosmos. The single timeline model presents a universe of elegant, predetermined order. The multiverse model offers a cosmos of infinite chaos and possibility. The grandfather paradox forces us to confront not just the mechanics of time travel, but the very nature of reality itself. Is the past a finished book, a film reel that can be watched but not edited, or is it a living narrative sensitive to intervention? The answers we lean towards say as much about our philosophy as they do about our physics. This idea of a single, unchangeable timeline finds its most rigorous scientific expression in the Novikov self-consistency principle. Named after the renowned Russian astrophysicist Igor Novikov, this principle isn't just a philosophical suggestion, it's a proposed law of physics. It asserts that if time travel to the past is possible, then the universe must be inherently self-consistent. Any actions taken by a time traveler were always a part of the timeline. In other words, you cannot create a paradox because the laws of physics simply will not allow it. The past is not a fragile thing that can be broken. It is a robust, finished structure, and your journey back would be just another brick in that wall, having always been there. To understand how this would work in practice, let's move away from grandfathers for a moment and consider a much cleaner, mechanical example that Novikov himself favored: the billiard ball. Imagine a billiard table with a wormhole or some other time machine device hovering just above it. This device is arranged so that a ball entering it is sent back in time by exactly 5 seconds. Now suppose you take a shot, you hit the cue ball and it's rolling toward the pocket, but it's also on a path that will take it directly into the time machine. The ball vanishes and reappears 5 seconds in the past, just in time to collide with its own past self. What happens in that collision? Our instinct might be to imagine a paradox. What if the newly arrived ball knocks its past self off course, preventing it from ever entering the time machine? But the Novikov principle says this is impossible. The collision must happen in the one and only way that ensures a consistent loop. The arriving ball won't prevent the past ball from entering the machine. It will hit it with just the right angle and force to ensure that it goes in. Perhaps the past ball was heading slightly off target, and the collision from the future gives it the precise nudge it needs. The event is a closed, self-contained loop with no beginning and no end. The ball's journey through time was always an integral part of its own history. There is no first time the event happened. It just is a stable, unchangeable fact of the universe. Applying this to a human traveler, the implications are both comforting and deeply strange. Let's return to that idea of trying to prevent your grandparents meeting. According to Novikov, you could certainly travel back in time. You could even find your grandfather, raise your weapon and pull the trigger, but the principle guarantees that you will fail. Not because of a lack of will, but because the universe is a master of subtle, intricate coordination. The gun will misfire, a passerby will bump into you. A sudden noise will startle you, or more poetically, your very attempt will set in motion the exact chain of events you hope to stop. In your effort to interfere, you might accidentally introduce them to each other. Your presence in the past was never an interruption, it was always the catalyst. This removes the paradox entirely, but it also paints a picture of a universe where free will is an illusion. Our choices feel real to us, but they are simply us acting out our predetermined part in a cosmic story that has already been written from beginning to end. This vision aligns with the block universe theory of time, which many physicists, including Einstein, found compelling. In this view, past, present, and future all exist simultaneously. The flow of time we feel is just a psychological artifact of our consciousness moving through this static four-dimensional structure. The Novikov self-consistency principle is the logical enforcement mechanism for such a universe. It ensures that every world line, even those twisted into closed loops, fits together without any contradictions. While this solves the logical problem of paradoxes, it challenges our deepest intuitions about causality and our ability to shape our own destinies, presenting a cosmos of elegant, unavoidable fate. Yet another compelling escape from the paradox trap comes not from enforcing a single history, but from embracing the idea of infinite histories. This is the domain of the many worlds interpretation of quantum mechanics, a theory that radically reimagines the very nature of reality. Proposed by physicist Hugh Everett in the 1950s, the many worlds interpretation offers a breathtakingly elegant, if dizzying, solution to the puzzles of time travel. It suggests that the universe doesn't have to choose between conflicting possibilities. It can simply realize them all. To grasp this, we need to step into the bizarre world of quantum mechanics, where particles can exist in a blur of multiple states at once, a phenomenon known as superposition. The classic example is Schrödinger's cat, a thought experiment where a cat in a box is simultaneously alive and dead until someone opens the box and observes it. The traditional Copenhagen interpretation of quantum mechanics says that the act of observation forces the system to collapse into one definite state: the cat is either alive or dead. Everett's revolutionary idea was to propose that no collapse ever occurs. Instead, at the moment of measurement, the universe itself splits. In one branch of reality, the observer finds a live cat. In another, completely separate but equally real branch, the observer finds a dead cat. Every time a quantum event has more than one possible outcome, the entire cosmos bifurcates, spawning new universes to accommodate every single possibility. Now apply this logic to time travel. According to the many worlds view, traveling to the past does not mean returning to your own past in your original universe. Instead, a closed time-like curve would act as a bridge connecting you to the past of a parallel universe, a universe that was identical to yours up until the moment you arrived. The moment you step out of the time machine, you become a new variable, a quantum event in your own right. Your very presence causes a new branching. In this new timeline, your actions are free from the constraints of your personal history. You could find your grandfather and prevent his meeting with your grandmother. The paradox is avoided because in this new branch you were never born. But your existence is not a contradiction. You are a visitor from a separate reality, and the history of this new universe simply unfolds with you as a foreign element. Your original timeline remains pristine and untouched, a separate thread in the vast tapestry of the multiverse. This transforms the concept of time travel from a historical edit into a form of cosmic emigration. You are not rewriting your own story. You are leaving your home universe and becoming a permanent resident of a new one. Every choice you make in the past doesn't alter a single timeline, but instead creates a cascade of new branches. Decide to share futuristic technology, you create a universe with that advanced knowledge. Decide to keep a low profile, you inhabit a timeline that remains nearly identical to your original, except for your anonymous presence. The power to change things is real, but the consequences are borne by the new realities you help create. This makes time travel an act of profound creation and exploration, hopping between branches of a limitless multiverse. The implications are staggering. It suggests that every possible history actually exists. There is a universe where the Roman Empire never fell, a universe where you took a different job offer, and a universe where every conceivable variation of every event is playing out. While this solves the logical problem of paradoxes with stunning simplicity, it also presents a cosmos of unimaginable scale and loneliness. Your actions in the past don't correct mistakes in your own life. They simply generate new worlds where those mistakes never happened for another version of you. This interpretation offers immense freedom at the cost of a certain existential weight, framing time travel not as a journey through one's own life, but as a voyage across the infinite landscapes of possibility. So far, our exploration of closed time-like curves has been rooted in the majestic framework of Einstein's general relativity. It paints a picture of a universe with a smooth, continuous fabric, where gravity is simply the geometry of curved spacetime. This is the realm of planets, stars, and black holes, a deterministic world where, if you know the exact state of the universe at one moment, you could, in principle, calculate its entire future and past. It's a classical view, beautiful and predictable, but when we push our inquiry to the absolute extremes, to the very environments where CTCs might form, we run headlong into a wall. This is the frontier where general relativity meets its greatest rival and its necessary partner, quantum mechanics, and the two do not get along. quantum mechanics governs the world of the incredibly small atoms, electrons, photons. Its reality is utterly different from the smooth cosmos of relativity. Here, certainty is replaced by probability. Particles don't have definite locations until they are measured. They exist as clouds of possibility described by wave functions. Energy comes in discrete, indivisible packets or quanta. It's a fuzzy, probabilistic, and often counterintuitive domain that has been spectacularly successful in explaining the behavior of matter and forces on a small scale. The problem is that these two pillars of modern physics, each proven correct in its own domain, are fundamentally incompatible when brought together. General relativity describes the force of gravity as the curvature of a smooth spacetime stage, while quantum mechanics describes the other three forces, electromagnetism and the nuclear forces, as being mediated by particles dancing on that stage. To truly understand what happens at the center of a black hole or in the first moments of the Big Bang, where both immense gravity and tiny quantum scales are at play, we need a single theory that unites them, a theory of quantum gravity. This clash is not just a technical detail for physicists to argue about. It is absolutely central to the fate of closed time-like curves. The solutions that allow for CTCs, like the Gödel universe or the region around a rotating black hole, are purely classical general relativity solutions. They ignore quantum effects entirely, but when we introduce quantum mechanics into the picture, the stability of these time loops is thrown into serious doubt. The vacuum of space, according to quantum field theory, is not truly empty. It's a seething foam of virtual particles constantly popping in and out of existence. In the bizarre geometry of a CTC, these quantum fluctuations could create a feedback loop of unimaginable power. Imagine a single photon traveling back in time. It could interact with its past self, and that interaction could be amplified with each cycle around the loop. The energy density could rapidly escalate to infinity, creating a cataclysmic instability that would either destroy the time loop or force the spacetime to reconfigure itself into a geometry that prevents time travel altogether. This is the essence of Stephen Hawking's renowned chronology protection conjecture. Hawking famously quipped that the universe must have a deep-seated aversion to time travel, a cosmic censorship that prevents paradoxes from ever occurring. His conjecture wasn't based on a fully fleshed-out theory of quantum gravity, but on a strong intuition from semi-classical gravity, an approach that tries to incorporate some quantum effects into a general relativity background. He argued that the build-up of quantum energy in a CTC would act like a wall of infinite energy, a physical barrier that makes time travel impossible. It's as if the universe has a self-correcting mechanism. Any attempt to create a time machine would trigger a quantum backlash that seals the door to the past shut. This is one compelling possibility, that quantum mechanics, not logic alone, is the ultimate guardian of causality, actively preventing the formation of paradoxes through physical law. However, the story might be even stranger. A complete theory of quantum gravity, such as string theory or loop quantum gravity, might not simply forbid time travel. Instead, it could radically redefine what it means. In these theories, the very concept of a smooth, continuous spacetime breaks down at the Planck scale, the smallest possible unit of length. Spacetime itself may be emergent, woven from more fundamental quantum entities like atoms weaving a fabric. In this view, the smooth geometry of general relativity is an approximation, a large-scale average of a discrete, grainy underlying reality. What does this imply for a closed time-like curve? A CTC is a global structure, a large looping path through spacetime. If spacetime is not fundamental, then such a large-scale path might simply not exist in the quantum description. The loop could be disrupted or made nonsensical by the discrete, granular nature of reality at its most basic level. The question, what happens to a particle on a CTC, might be like asking, what is the temperature of a single atom? a question that loses its meaning when you drill down to the fundamental building blocks. This leads to a thrilling, albeit highly speculative, idea. Perhaps CTCs are not traversable by macroscopic objects like people or spaceships, but quantum information itself might be able to loop back. Some research into quantum gravity suggests that while large-scale paradoxes are prevented, there could be microscopic, self-consistent time loops that allow for quantum states to influence their own past. This wouldn't allow you to meet your grandfather, but it could enable bizarre computational possibilities or even play a role in the universe's own initial conditions. The final answer remains locked away, waiting for the discovery of a complete theory of quantum gravity. Until then, closed time-like curves stand at the crossroads of our deepest physical theories, a tantalizing possibility born from the geometry of relativity, but whose ultimate fate will be decided by the quantum laws that govern the very fabric of reality. This brings us directly to one of the most famous and compelling arguments against the possibility of time travel, championed by the legendary Stephen Hawking. Frustrated by the theoretical loopholes that seem to allow for journeys to the past, Hawking proposed what he called the chronology protection conjecture. It's a powerful idea, essentially suggesting that the universe has a built-in immune system designed to protect the sequence of cause and effect. Hawking wasn't just making a philosophical point, he was arguing that a specific physical mechanism, rooted in the laws of quantum mechanics, would actively sabotage any attempt to create a time machine. He even engaged in a bit of playful, real-world experimentation to make his case. Hawking once held a party for time travelers at the University of Cambridge. There was a catch, though. He only sent out the invitations after the party had already taken place. His reasoning was flawless. If time travel is ever invented in the future, then future generations would have access to the historical record, see the invitation, and could easily pop back to attend. He laid out champagne and hors d'oeuvres and waited. Nobody showed up. While this wasn't a rigorous scientific proof, it was a charming and effective demonstration of his point. If time travel were possible, shouldn't our present be teeming with tourists from the future? The empty room seemed to suggest that, for whatever reason, the past remains a destination that is permanently closed for visitation. But Hawking's real contribution was theoretical. He delved into the physics of what would happen at the very moment someone tried to create a closed time-like curve. His work focused on the quantum nature of empty space. We often think of a vacuum as being truly empty, but quantum field theory reveals that it's actually a vibrant, seething sea of activity. At the tiniest scales, pairs of virtual particles constantly flicker into and out of existence, borrowing energy from the vacuum for an infinitesimally short time before annihilating each other and paying the energy back. This isn't just a mathematical quirk, it's a verified phenomenon with real-world effects. Now, imagine trying to form a time loop in a region of spacetime. Hawking realized that these quantum vacuum fluctuations would be catastrophic for the stability of the loop. A single virtual particle pair could be swept up in the forming curve. One particle might travel forward in time while its partner is sent backward. They could then meet each other again at an earlier point, interact, and the process could repeat. With each cycle around the loop, the energy of these quantum fluctuations would feed back on itself, amplifying over and over. This wouldn't be a gentle buildup. The calculations suggested it would lead to a divergence, an energy density that skyrockets to infinity right at the moment the time loop tries to snap closed. It would be like an audio feedback screech where a sound from a speaker is picked up by a microphone, amplified, and sent back through the speaker, creating an ear-splitting loop, but on a cosmic scale with the very fabric of reality. This infinite surge of energy would either destroy the nascent time machine outright or force the space-time to reconfigure itself into a new geometry where time travel is impossible. In essence, the universe would rather tear itself apart than allow a paradox to happen. This is physics policing itself, a fundamental law stepping in to preserve the logical order of cause and effect that our reality depends on. Of course, all of this cosmic speculation about rotating universes and wormholes can feel incredibly distant, something for future generations of astronauts to ponder. But what if we could bring these mind-bending questions down to Earth, testing the logic of time travel not with starships, but with some of the most advanced technology in a modern physics laboratory? This is precisely what is happening right now through the incredible power of quantum simulation. Scientists are not building actual time machines. Instead, they are creating miniature, analog universes inside carefully controlled quantum systems to ask a profound question. If time travel were possible, how would it really work? The key to this approach lies in a powerful concept in physics: the idea that wildly different systems can be governed by the same underlying mathematics. Think about the way a vibrating guitar string and the waves in a pond can both be described by similar wave equations. The physical realities are completely different. One is a tight chord, the other is water, but the mathematical language that predicts their behavior is virtually identical. Researchers are applying this same principle to closed time-like curves. They realized that the bizarre, self-referential logic of a particle influencing its own past has a striking mathematical cousin in the strange world of quantum mechanics, particularly in the way quantum states can become entangled and interact with themselves. So, instead of trying to warp the fabric of spacetime, which requires energies far beyond our reach, they create a quantum system that mimics or simulates the essential rules of a CTC. One of the most fascinating experiments in this area comes from the University of Queensland. The researchers there used particles of light, photons, to play the role of a time-traveling quantum bit or qubit. In their ingenious setup, a single photon doesn't actually travel through time. Instead, its quantum state, a fragile combination of possibilities like its polarization, is sent on a journey through a circuit that forces it to interact with an older version of itself. This is the simulation. The circuit is designed so that the photon's final state is dependent on what its state was at an earlier point in the experiment, creating a closed loop of influence that perfectly mirrors the self-consistency required by a real CTC. It's a digital, quantum analog of Novikov's billiard ball. The results were stunning, and they provided a dramatic hint about how the universe might handle paradoxes. When the researchers programmed the photon to do something that would create a logical inconsistency, like changing its past polarization in a way that would prevent it from having the polarization needed to make the change, the system simply broke down. The photon didn't emerge in a paradoxical state, it just failed to produce a result at all. However, when the experiment was set up to allow for a self-consistent solution, the photon's quantum state reliably settled into that one stable loop. It was as if the laws of physics, even in this simulated environment, were actively selecting for consistency, weeding out any possibility that would lead to a logical contradiction. This doesn't prove that real CTCs exist, but it strongly suggests that if they do, the universe would likely enforce the Novikov principle, allowing only those histories that make logical sense. More recent work has pushed this even further, exploring the idea of simulating time travel within the many worlds interpretation. In one experiment, scientists used a quantum computer to model a qubit traveling back in time to perform a specific task. In a universe with a single timeline, certain tasks are mathematically proven to be impossible if you only get one chance, as they would create an inconsistency. But in the simulation, when the researchers allowed the qubit's journey to branch into multiple parallel realities, as it would in a many-world scenario, the impossible task suddenly became possible. The qubit could gather information from one branch of a quantum decision and use it in another, effectively accomplishing a goal that would be forbidden in a classical, single-timeline world. This hints that if our universe is truly a multiverse, then time travel might not be about changing the past, but about harnessing the computational power of infinite parallel worlds. These lab-based simulations are not about building a working DeLorean. They are something perhaps even more profound. They are tools for stress testing the very laws of physics. By creating these analog systems, physicists are conducting archaeology on the logical structure of the cosmos, probing the boundaries between possible and impossible. They are asking whether the rules that prevent paradoxes are just suggestions, or if they are enforced with the ironclad certainty of a physical law. Each experiment, each flickering quantum state settling into a consistent loop, is a tiny piece of evidence in the greatest detective story of all, figuring out the fundamental rules that allow our universe, with its clear arrow of time and reliable causality, to exist at all. Now, let's take all of these abstract paradoxes and thought experiments and anchor them to a tangible, almost cinematic scenario. Imagine you have a blueprint for a time machine. Not a vague idea, but a complete step-by-step set of schematics with equations and material specifications. The problem is you didn't invent it. You received it from your future self, who traveled back in time to deliver it to you. Your sole mission, the only reason you dedicate your life to physics and engineering, is to build this device exactly as specified, so that one day you can go back and give the plans to your younger self. This is the ultimate bootstrap paradox, a loop where the information, the blueprint, has no discernible origin. It simply exists, a timeless, self-created object. In physics, this idea is so strange that it has earned a nickname, the Jinn particle, a nod to the mythical beings that appear from nowhere. This scenario forces us to confront one of the most sacred principles in all of science, the conservation of information. In the world of classical physics, we're familiar with the conservation of energy, and mass energy cannot be created or destroyed, only transformed. The conservation of information is a more profound, quantum-level extension of this idea. It states that the complete information about a physical system, the unique configuration of every particle, is preserved over time. If you could know the exact state of every particle in a burning log, the theory goes you could, in principle, reverse the process and reconstruct the log from the smoke and ashes. Information is never truly lost, it just becomes incredibly difficult to read. A black hole was once thought to be the ultimate information shredder, but even there, physicists now believe the information is somehow preserved on the event horizon. The universe seems to keep impeccable records, so what happens when a blueprint for a time machine pops into existence from nowhere? It appears to be a glaring violation of this principle. The information in those schematics wasn't transformed from another state. It wasn't encoded in starlight or deduced from natural laws. It was simply inserted into the timeline. It has no causal origin. From the perspective of someone outside the loop, it's as if the universe has a glitch, a piece of data that was never written but always exists. This is deeply troubling because our entire understanding of physics is built on causality, the idea that events have causes that precede them. A universe where information can appear without a cause would be a universe where prediction and understanding become fundamentally impossible. One way to resolve this is to apply the Novikov self-consistency principle with ruthless logic. In a single, predetermined timeline, the blueprint was never created, it was always there. The loop itself is the origin. The information isn't being created anew each cycle. It's a fixed, eternal feature of the cosmos. Think of it not as a line with a beginning and end, but as a circle, like a snake eating its own tail. There is no point on the circle that is the start. The information is just part of the loop's immutable structure. In this view, conservation isn't violated because the information was never not there. It is conserved within the closed system of the timeline itself. This preserves the law, but at the cost of introducing a bizarre type of object, a self-existing fact that has no creator. However, the quantum revolution offers a different, perhaps even stranger, way out. The many worlds interpretation can dissolve the bootstrap paradox entirely. In this multiverse model, the blueprint does have an origin. Perhaps in the original timeline, a brilliant scientist, let's call her Dr. Eva, actually invented the time machine through decades of painstaking research. When she finally used it to travel to the past, her arrival created a new branch universe. In this new branch, she gives the plans to her younger self. For that younger version, the plans appear to have no origin, but that's only because she is unaware of the parent universe where the real hard work of invention took place. The information wasn't created from nothing, it was imported from another reality. The paradox is an illusion born of a limited perspective confined to a single timeline. The Jinn particle is just a tourist from a world next door. But what if we push even further? What if the very act of a particle interacting with its own past is not a bug, but a feature that the universe can actually exploit? This is where we step into the speculative realm of post-selection, a concept in quantum mechanics where you only consider the outcomes of an experiment that satisfy a specific condition. Applied to time travel, it suggests that the universe might not just avoid paradoxes, it might actively use time loops to perform computational tasks that are otherwise impossible. A particle traveling back in time could be post-selected to only complete its journey if it arrives in a state that is consistent with a desired outcome. It's a cosmic feedback system that fine-tunes reality. In this highly theoretical framework, a bootstrap paradox isn't an error, it's a logical circuit. The information in the time machine blueprint wouldn't have an origin story because its origin is the loop itself. A self-consistent solution the universe has settled into to achieve a specific, if inscrutable, goal. The implications are staggering, suggesting that causality might not be a rigid chain of events, but a flexible web of consistent connections where the future can quite literally shape the past to bring about its own existence. This mind-bending connection between closed loops in time and computational power leads us to one of the most speculative and thrilling intersections of modern physics. What if the bizarre logic of a closed Timelike curve could be harnessed not for travel, but for calculation? Some theorists have proposed that the very structure of a CTC, with its ability to create feedback loops where cause and effect intertwine, could act as the ultimate processing unit, capable of solving problems that would stump even the most powerful supercomputers for centuries. The key lies in a class of problems that are easy to state but agonizingly difficult to solve with conventional, step-by-step logic. Consider the task of finding the prime factors of an astronomically large number. This is the foundation of much of our digital security. Your bank details, your private messages, they are often protected by encryption that relies on the simple fact that while it's easy to multiply two large prime numbers together, it's incredibly time-consuming to reverse the process and figure out what those original primes were. A classical computer must essentially try possibilities one after another, a process that could take longer than the age of the universe for a sufficiently large number. A quantum computer, leveraging the strange properties of superposition and entanglement, can attack this problem differently, testing many possibilities simultaneously. But a computer that could exploit a closed Timelike curve might perform a feat that seems like pure magic. It could find the answer instantly. The theoretical mechanism for this is as strange as the result. Imagine a computer whose output is connected directly to its own input through a CTC. You feed the computer a random guess for the solution to a problem, like a random guess for the prime factors of a large number. The computer processes this guess and sends the result back in time to become its own starting point. Now, here is where the consistency principle of Novikov becomes a computational tool. The universe, demanding a self-consistent loop, would force the computer's output to be perfectly consistent with its input. The only way for this to happen is if the guess that goes into the computer is already the correct answer. The computer's processing doesn't find the answer through calculation. It forces the timeline to collapse into the one reality where the answer was always known. It's a form of cosmic cheating where the computer uses the requirement of a paradox-free universe to pinpoint the solution in a single operation. The calculation is not performed, it is preordained by the need for logical consistency. This idea was formally explored by physicist David Deutsch, who showed that such a computer, if it could be built, would belong to a class of machines of unimaginable power, far beyond even the theoretical limits of quantum computers. It could solve not just factoring, but a whole range of problems in the complexity class known as NP-complete. These are problems where verifying a solution is easy, but finding one from scratch is hard, like figuring out the most efficient route for a delivery truck visiting hundreds of cities. For a CTC computer, the difficulty vanishes. The machine would simply output the correct optimal route every time, because any other output would create an inconsistent loop that the laws of physics would prohibit. The implications of this are staggering, pointing to a deep and perhaps fundamental link between the nature of time, information, and the limits of what is computable. It suggests that causality itself might be the ultimate resource for computation. In our everyday, open timeline universe, we are limited to calculations that move forward step by step. But in a universe that permits closed time-like curves, the computational process could loop back on itself, creating a form of logical resonance that instantly converges on the correct answer. This isn't just a faster computer, it's a different paradigm altogether, one where the flow of time is not a barrier but a tool. Of course, this remains a highly speculative thought experiment. Building a device that manipulates spacetime to this degree is far beyond our current or foreseeable capabilities. However, it serves a profound purpose. By pushing our theories to their absolute limits, we gain a deeper understanding of the laws that govern our reality. The study of CTCs and computation forces us to ask, are the laws of physics and the laws of logic ultimately the same thing? Is the reason we cannot build a time travel computer the same reason we cannot square a circle because it is a logical impossibility? Or does this theoretical possibility hint at a deeper layer of reality where information and spacetime are so deeply intertwined that computation and cosmology become one and the same? This line of inquiry doesn't just explore the potential of future technology, it probes the very foundations of a predictable, computable universe. Yet, for all our focus on the physics and the paradoxes, there's a dimension to this possibility we've yet to fully confront, the human dimension. What would it actually feel like to be the person who steps through that loop? The technological and logical hurdles are immense, but the psychological burden might be the most profound barrier of all. Stepping outside the linear flow of time we've always known could unravel the very fabric of our identity, which is so deeply woven from the threads of memory and anticipation. Our sense of self is a story we tell ourselves, a narrative that begins in the past and arcs toward a future. But what happens to that story when the sequence of chapters is no longer fixed? Consider the crushing weight of knowledge. If you were to travel to the future and learn a devastating truth, the date of your own death, the failure of a lifelong dream, a global catastrophe you are powerless to stop, how would you live with that certainty? The anxiety of not knowing the future is a fundamental part of the human condition. It's what gives our choices meaning and our hopes their power. To have that uncertainty replaced with an immutable fact could be a prison of the mind, leading to a profound existential dread. Every action, every decision would be shadowed by the knowledge of how it all turns out, potentially draining life of its spontaneity and joy. You might become a passive spectator in your own life, simply acting out a script you've already read. This echoes powerfully in films like Arrival, where linguist Louise Banks learns an alien language that rewires her brain to perceive time not as linear but as a whole. She gains the ability to remember events from her future as clearly as those from her past. This gift is also a curse. She experiences the deep love for a daughter she has not yet conceived, and simultaneously the agonizing grief of that daughter's premature death. Her entire life becomes a simultaneous experience of joy and sorrow, of beginnings and endings. She must choose to walk the path anyway, to embrace the beautiful moments fully aware of the heartbreak that awaits. This isn't a triumph over time, but a heartbreaking reconciliation with it, a portrait of the immense emotional fortitude required to bear the burden of foresight. Beyond the weight of knowledge lies the potential for a complete identity crisis. If you interact with your past self, which you is the real one, is the older, weary traveler the authentic self, while the younger version is just a memory? Or does meeting your future self irrevocably alter the younger you, creating a feedback loop where your identity is constantly being redefined by an encounter with a version of yourself that only exists because of that very encounter? This could lead to a terrifying dissociation, a feeling of being untethered from a stable reality. Your memories might no longer feel like your own. They could become artifacts from a timeline that no longer exists, or previews of a future that has yet to unfold. The core continuity of consciousness, the thread that makes you you, could snap under the strain. And then there is the moral weight, particularly if you find yourself trapped within a causal loop, like the bootstrap paradox of the time machine blueprint. If your entire life's work is not the product of your own creativity and effort, but merely the fulfillment of a preordained task passed down from a future self, what does that say about your free will? Your sense of agency, the belief that you are the author of your own life, could evaporate. You might feel like a puppet performing a play written by a mysterious director who is also you. This could lead to a deep-seated resentment or a nihilistic apathy. If your choices are not truly your own, if they are just cogs in an inescapable machine, then what is the point of striving, of loving, of caring? The psychological safety we derive from believing in our ability to shape our destiny would be shattered. Ultimately, the greatest challenge of closed time-like curves may not be bending spacetime, but preserving the human mind within the bend. The physics suggests mechanisms for consistency, like the Novikov principle, that prevent logical paradoxes, but there is no law of physics that protects against despair, that guards against the fragmentation of the self. A journey to the past or future might not tear the universe apart, but it could very well tear a person apart. It forces us to ask whether our linear experience of time, for all its limitations, is not a constraint but a necessary condition for sanity, for meaning, and for the fragile, beautiful project of building a life. We have journeyed through the mind-bending physics and the brain-twisting paradoxes, but now we must confront what might be the most difficult terrain of all, the human heart. If closed time-like curves were more than a theoretical possibility, if they became a practical technology, we would instantly be faced with ethical dilemmas of a scale and complexity that humanity has never before encountered. This isn't just about the physics of can we, but the profound morality of should we. The power to reach into the past and alter the tapestry of history is arguably the greatest power imaginable, and with it comes a responsibility so immense it's almost impossible to comprehend. The first and most urgent question is one of governance. Who in all the world would be trusted with the keys to time? Would it be a single nation claiming sovereignty over the past for its own strategic advantage? An international body like a vastly empowered United Nations attempting to forge a global consensus on how history should be managed? Or would it be kept secret, a tool for a shadowy elite? The potential for abuse is staggering. Imagine a regime sending agents back to subtly influence an election to ensure a favorable political landscape for centuries to come. They wouldn't need to change the outcome of a world war. Simply altering a single close parliamentary vote or discrediting a key figure at a pivotal moment could cascade into a future where their ideology is unchallenged. The very concept of a fair and open historical record would vanish, replaced by a curated past designed to legitimize the present power structure. This isn't just changing history, it's the ultimate form of censorship, erasing the factual foundation upon which we build our understanding of the world. This leads directly to the most emotionally charged ethical dilemma, the prevention of tragedies. It is a natural human impulse to want to stop terrible events from happening. Who wouldn't want to prevent the assassination of a visionary leader, to avert a genocide, or to issue a warning about a natural disaster that claimed thousands of lives? The intention is unimpeachably good, but this is where we run headlong into the "who decides" problem. One person's tragedy is another's pivotal historical moment. Would preventing the rise of a brutal dictator be an unambiguous good? Perhaps, but what about the technological innovations, the social solidarity, or the political lessons that emerged from the struggle against that very regime? The butterfly effect would be incalculable. A well-intentioned mission to save a single life could inadvertently alter the circumstances that led to a future medical breakthrough, costing millions of lives down the line. We would be playing a game of cosmic chess with an infinite board, unable to foresee the consequences of even the smallest move. This dilemma is powerfully explored in stories like Stephen King's 11/22/63, where the protagonist discovers that preventing the Kennedy assassination leads to a dystopian future far worse than the one he knew. The narrative forces us to ask whether we have the right to trade one set of lives for another, to make a decision that effectively erases an entire future timeline with all the people, loves, and achievements in it, in favor of one we deem more acceptable. This isn't just changing the past, it's an act of existential violence against a potential future. Every baby born in the altered timeline is a baby that will never be born in the original. Are we playing God, deciding which generations get to exist and which are consigned to the void of unrealized possibility? The moral weight of such a choice is unbearable for any individual or committee to hold. And then there are the personal, intimate ethical questions that go beyond grand historical narratives. What about the temptation to correct your own personal mistakes? It seems harmless enough to go back and tell your younger self to invest in a certain company or to avoid a specific heartbreak, but this injects a corrosive element into the human experience. Our mistakes, our failures, our regrets, they are not just setbacks, they are the forge in which our character is shaped. A life lived without error, without unintended consequences, would be a life without growth, without resilience, without the hard-won wisdom that comes from navigating difficulty. The very things that make us who we are could be smoothed away, leaving a shallower, less interesting version of ourselves. The ethical challenge here is about the value of an authentic life, lived forward with all its imperfections, versus a curated existence built on endless second chances. Do we have a responsibility to our own journey to let it unfold naturally, even with its pain? Ultimately, the ethics of time travel force us to define what we value most about the human condition. Is it the pursuit of a perfect, painless world, no matter the cost to our autonomy and the integrity of history? Or is it the sanctity of the journey itself, the unbroken chain of cause and effect that gives our actions meaning, our relationships depth, and our stories their power? To introduce time travel is to introduce the ultimate cheat code into reality. And as any gamer knows, once you start using cheat codes, the game itself often loses its purpose and its joy. The greatest ethical imperative might be a surprising one: to leave the past alone, not because we can't touch it, but because we respect the fragile, beautiful, and consequential nature of a universe where our choices, for better or worse, truly matter. Long before physicists were scribbling equations about closed time-like curves on blackboards, storytellers were already grappling with the profound implications of journeying through time. using the power of narrative to explore the very paradoxes and possibilities we've been discussing. The journey of this idea in our collective imagination begins in earnest with H.G. Wells and his seminal 1895 novel, The Time Machine. Wells, a writer deeply engaged with the scientific debates of his day, made a crucial conceptual leap. He didn't rely on magic or supernatural sleep. He envisioned time as a fourth dimension, and his machine simply traveled along it. This was a radical shift, framing time travel as a form of navigation, a technological feat. His time traveler journeys to the far future, witnessing the evolution and eventual decay of humanity. While Wells wasn't dealing with the looping paradoxes of CTCs, he established the foundational idea that time could be a landscape to be traversed, setting the stage for all the science fiction that would follow, and in many ways anticipating the geometric view of spacetime that Einstein would propose just a decade later. As the 20th century progressed and the complexities of relativity seeped into public consciousness, time travel stories grew more sophisticated, beginning to wrestle directly with the psychological and causal nightmares we've outlined. A landmark in this evolution is the 1962 French short film La Jetée, a story composed almost entirely of still images. It presents a future where survivors of a world war living underground experiment with time travel, sending a man back to his own childhood memories to seek help. The narrative is a heartbreaking exploration of the Novikov self-consistency principle before it had that name. The protagonist's entire journey is looped. His haunting childhood memory of a man dying on an airport pier is in fact the memory of his own death. He is trapped in a predestined cycle, his actions always having been part of the timeline. There is no changing the past, only fulfilling it. This poetic, tragic film demonstrates how art can capture the eerie elegance of a deterministic universe where time travel doesn't grant freedom, but reveals a cruel, inescapable fate. This theme was powerfully expanded for a wider audience in Terry Gilliam's 1995 film 12 Monkeys, a loose adaptation of La Jetée. Here, the protagonist, James Cole, is sent from a ravaged future to investigate the origins of a deadly virus. The film masterfully plays with the audience's perception of sanity and reality, as Cole's memories and dreams blur with his experiences in the past. 12 Monkeys brilliantly illustrates the bootstrap paradox. The very act of sending Cole back ultimately leads to the creation of the army of the 12 Monkeys and, inadvertently, the release of the virus itself. The information about the virus's origin has no true beginning. It's a closed loop of cause and effect. The film forces us to confront the futility of Cole's mission. He isn't there to change history, but to become a vital part of it, a cog in a machine whose outcome was fixed before he even began. In stark contrast to these grand, fatalistic narratives, the 21st century brought us a new kind of time travel story, one obsessed with the gritty, technical mechanics of the loop. Shane Carruth's 2004 indie film Primer is the ultimate example. Made on a minuscule budget, it presents time travel not as a fantastical adventure, but as a tedious, dangerous engineering project. Two engineers accidentally discover a way to create a time loop using a box that allows them to travel back a few hours each day. The film is renowned for its hyper-realistic approach. The characters draw diagrams, argue about power consumption, and grapple with the exhausting physiological effects of doubling their own timelines. Primer is a direct cinematic analog to the wormhole time machine we described. It visualizes the practical consequences of a small-scale CTC, showing how even a limited loop can lead to horrific paradoxes, betrayal, and the complete fragmentation of identity as the characters' copies multiply and their agendas conflict. It's a cautionary tale about the unmanageable complexity that arises when you can interact with your own recent past. Most recently, Christopher Nolan's Tenet took the concept of time inversion to its logical, blockbuster extreme. The film introduces a world where objects and people can have their entropy reversed, moving backward through time relative to the forward-flowing world. This creates breathtaking action sequences where bullets fly back into guns and cars chase each other in opposing temporal directions. Tenet is less about philosophical predestination and more about the mind-bending physics of a universe where backwards causation is a tangible weapon. The protagonist literally fights his own past self, a visceral depiction of the grandfather paradox in action. The film's central theme, "What's happened, happened," is a direct nod to the Novikov principle, suggesting a single, immutable timeline. Yet, it also introduces the tantalizing idea of a parallel, hidden war being fought across time, pushing the concept to its limits and demanding multiple viewings to untangle its intricate, self-referential plot. These cultural depictions do more than just entertain. They shape our understanding and frame the public's questions about time travel. Wells gave us the vehicle, La Jetée, and 12 Monkeys showed us the tragic, inescapable loops. Primer revealed the terrifying practicalities, and Tenet visualized the warped physics of an inverted reality. Together, they form a rich dialogue with the scientific community, exploring the emotional weight and logical consequences of closed time-like curves in a way equations alone never could. They remind us that the ultimate challenge of time travel may not be mastering the fabric of spacetime, but surviving the impact of that knowledge on the human mind and spirit. But let's suppose for a moment that the fundamental physics aligns in our favor, that the Novikov principle holds true and the quantum vacuum remains stable. We are still left with the Herculean, almost unimaginable task of construction. The first and most obvious hurdle is energy. To warp spacetime into a closed loop, you need to concentrate an astronomical amount of mass energy into a tiny region. General relativity tells us that spacetime curvature is directly related to the density of energy and momentum. Creating a wormhole throat or twisting spacetime into a CTC would require energy densities that make a hydrogen bomb look like a firecracker. We're talking about concentrations of energy comparable to that of an entire star, compressed down to a microscopic point. Some theoretical estimates suggest you might need to harness the total energy output of a star like our Sun for years, or even manipulate the energy of a supernova just to create a traversable wormhole a single meter in diameter. Our entire global energy production is a vanishingly small whisper compared to the cosmic roar needed to stitch the fabric of time back onto itself. This brings us to one of the most speculative yet essential ingredients in many time machine designs: exotic matter. Not matter that is strange or rare, but matter with a truly bizarre property, negative energy density or negative pressure. Think about what gravity normally does. It attracts. Positive mass and energy curve spacetime inward, creating the gravity wells that hold planets in orbit. To keep a wormhole open against its own tendency to pinch shut into a singularity, you need something that pushes spacetime apart, creating a kind of anti-gravitational effect. Exotic matter would provide this repulsive gravity. The problem is, we have no conclusive evidence that such matter exists in the stable, macroscopic quantities required. In the quantum world, the Casimir effect demonstrates that regions of negative energy density can exist between two closely spaced plates, but these are fleeting, microscopic effects. Amassing enough of this exotic substance to line a wormhole throat is like trying to build a dam with a material we've only ever seen in individual molecules of water. It's a theoretical possibility that highlights just how far beyond our current material science such a project would be. If manipulating wormholes seems daunting, then the idea of engineering with cosmic strings is on an entirely different scale of impossibility. Remember, these are hypothetical cracks in the universe, filaments of energy left over from the Big Bang, with the mass of a mountain range packed into every inch of their infinite length. The sheer scale of the engineering is beyond human comprehension. First, you would need to find two such strings, a discovery that would itself revolutionize cosmology. Then you would need to figure out a way to maneuver them. We are talking about objects with astronomical mass, moving them at velocities approaching the speed of light to create the necessary frame-dragging effects. The forces involved would be titanic, capable of tearing solar systems apart. It would be like trying to weave a tapestry using galactic clusters as your loom, a project for a civilization that has mastered not just a planet or a star, but the dynamics of galaxies themselves. This isn't engineering as we understand it. It's a form of cosmic landscaping that redefines the word. When we step back and look at the totality of these challenges, the astronomical energy requirements, the search for mythical forms of matter, the manipulation of primordial universe-scale structures, it becomes clear that building a time machine is not merely a next-step technology. It is not like progressing from the first airplane to a jetliner. It is a qualitative leap that seems to belong to a hypothetical class Roman II or Roman III civilization on the Kardashev scale, a civilization that harnesses the power of stars or even entire galaxies. For humanity, with our technology still tethered to a single, fragile planet, the project of constructing a closed time-like curve is not just far future. It is perhaps the ultimate engineering feat, a testament to how the universe guards its most profound secrets not with locks, but with requirements of almost unimaginable magnitude. The physics might whisper that it's possible, but the engineering shouts that it is, for any civilization we can envision, effectively impossible. So, if building a time machine is a project for gods, could the universe itself have crafted these temporal loops naturally? Could closed time-like curves be out there already, not as engineered constructs, but as features of the cosmic landscape waiting to be discovered? To explore this, we must venture into the most extreme environments physics allows, places where gravity becomes so overwhelming that it twists the fabric of reality into knots. The most promising candidates for such natural time machines are not gentle rotations like Gödel's universe, but the violent, chaotic hearts of collapsed stars and other theoretical monstrosities. Our first and most compelling destination is the interior of a rotating black hole. A standard black hole, described by Karl Schwarzschild's solution, is a simple, terrifying point of infinite density shrouded by an event horizon, a point of no return. But our universe is dynamic. Most stars and the black holes they collapse into are spinning. In the 1960s, physicist Roy Kerr found a solution to Einstein's equations that describes such a rotating black hole, and it is far stranger and more complex than its stationary cousin. A Kerr black hole doesn't have a singular point at its center. Instead, its immense rotation flings the mass into a ring-shaped singularity. This isn't a point you could hit, but a ring you could, in theory, pass through. The geometry inside the event horizon of a Kerr black hole becomes incredibly warped. The rotation creates such severe frame dragging that spacetime itself is pulled into a whirlpool-like motion. Within this chaotic inner region, the equations of general relativity predict the existence of closed time-like curves. An object surviving the journey through the event horizon could, in principle, find a path that loops back on itself in time, allowing it to revisit its own past. However, and this is a monumental however, this region is wildly unstable. It's shielded by not one, but two event horizons, and the area between them is thought to be filled with a lethal bath of high-energy radiation. Furthermore, most physicists believe that the ring singularity itself would be surrounded by a region of infinite tidal forces or a phenomenon called a Cauchy horizon, a boundary beyond which predictability breaks down completely. Reaching the theoretical CTC zone would likely be impossible. Any matter entering would disrupt the delicate geometry, causing the time loops to vanish almost instantly. So while the Kerr solution mathematically permits time travel, it's widely considered a mathematical curiosity, a ghost in the machine of relativity that is physically inaccessible. Another fascinating, though even more speculative, natural candidate is a theoretical object known as a Tipler cylinder, proposed by physicist Frank Tipler in the 1970s. Imagine a cylinder made of an unimaginably dense material, perhaps the length of a star system and as massive as a sun, spinning at a significant fraction of the speed of light. According to Tipler's calculations, the sheer mass and rapid rotation of this colossal object would warp spacetime around it in a very specific way. The twisting motion would drag the fabric of spacetime along with it, like a spoon stirring a vast pot of honey. If you were to approach this cylinder and follow a very precise spiral path around it, you could find yourself on a closed time-like curve. Your future light cone, the set of all points in spacetime you could possibly reach, would be bent by the cylinder's rotation until it overlapped with your past. You could literally fly your spaceship in a circle around the cylinder and return to the exact moment you started. It's an elegant idea, but it comes with two show-stopping requirements. First, the cylinder must be infinitely long. A finite cylinder would not produce the necessary spacetime distortion to create a CTC. Second, and perhaps more critically, the cylinder would need to be constructed from matter with negative energy density to prevent it from collapsing under its own immense gravity into a black hole. As we've discussed, such exotic matter is purely hypothetical. Therefore, while the Tipler cylinder is a brilliant piece of theoretical work that demonstrates how rotation and mass could generate time loops, it's almost certainly not a physical object that exists in our universe. This leads us to the crucial question: if these structures are mathematically possible but practically unattainable, why do most physicists relegate them to the realm of mathematical curiosities rather than serious predictions? The answer lies in a concept known as cosmic censorship, proposed by Roger Penrose. This is not a proven law but a widely held conjecture that the universe abhors naked singularities. A singularity is a point where the laws of physics break down, and a naked singularity is one that is not hidden behind an event horizon. Cosmic censorship suggests that nature always dresses singularities in an event horizon, preventing their unpredictable physics from affecting the wider universe. The interiors of black holes, where CTCs might lurk, are safely hidden behind these horizons. The ring singularity of a Kerr black hole is nominally naked, but it's generally believed that instabilities would clothe it at the moment of formation. Similarly, the ends of a finite Tipler cylinder would likely expose singularities. The prevailing view is that any realistic process of gravitational collapse or cosmic formation would inevitably produce an event horizon, shielding the cosmos from the paradoxes and infinities that naked singularities and their associated CTCs would unleash. In other words, the universe seems to have a built-in cleanup crew that ensures that the wild, lawless regions where time travel might be possible are permanently locked away from us, hidden behind impenetrable walls of gravity. So, while the mathematics of general relativity is rich enough to contain the seeds of time loops, the physics of our actual universe appears to include mechanisms that consistently prune those seeds before they can ever sprout. But this conversation about loops in time and self-consistent histories inevitably leads us to a much older, more profound debate about the very nature of time itself. Is it a river forever flowing from the past to the future, or is it a frozen landscape where every moment exists eternally? To understand the philosophical weight of closed time-like curves, we need to step back from the blackboards and examine two fundamentally different ways humanity has conceived of time, views that philosophers label the A theory and the B theory of time. The A theory is the view that feels most natural to us. It's the perspective of our direct, lived experience. In this view, time is dynamic and flowing. There is a special, privileged moment we call the present. The future is open, a realm of possibilities that has not yet happened, and the past is fixed, a collection of events that are gone forever. This is the world of becoming, where events come into existence as the present moment marches forward. Think of it like a spotlight moving across a dark stage. The part of the stage illuminated by the spotlight is the present. The part it has already passed over is the past, now in darkness, and the part it has yet to reach is the future, still unseen. This view aligns with our deepest intuitions about free will and responsibility. We feel we can shape the future precisely because it hasn't been written yet. Our regrets and nostalgia for the past stem from the belief that those moments are truly lost. The theory presents a universe where change is real, and the passage of time is an intrinsic feature of reality. In stark contrast stands the B theory of time, often called the block universe model. This view, which finds strong support in Einstein's theory of relativity, argues that the flow of time is an illusion, a trick of human consciousness. In the block universe, past, present, and future all exist equally and permanently. There is no special now. The universe is a static, four-dimensional block where spacetime events are just fixed locations. From this perspective, your birth, your reading of this sentence, and your eventual death are all equally real, just as Paris, Tokyo, and New York are all real places on a map. The feeling of time passing is just our conscious awareness moving along our world line from earlier events to later events, like a train moving along a track that is already fully built. This view was famously summarized by Einstein himself, who, upon the death of his friend Michel Besso, wrote, "Now he has departed from this strange world a little ahead of me." That means nothing. People like us who believe in physics know that the distinction between past, present, and future is only a stubbornly persistent illusion. So where do closed time-like curves fit into these two competing worldviews? For the theorist, a CTC is a profound and terrifying anomaly. A universe with a flowing time that somehow loops back on itself is a logical nightmare. How can the future, which hasn't happened yet, influence the past, which is already fixed and gone? It would be like a river suddenly flowing uphill, creating a whirlpool that connects its downstream flow to its upstream source. This seems to violate the very essence of the theory's sequential, becoming-based reality. The existence of a CTC would force the theorist to either abandon the idea of a single, objective flow of time, or to accept that time travel creates a sort of bubble where local causality is broken, a notion that many find deeply unsatisfying. For the B theorist, however, a closed time-like curve is not a paradox at all. It is simply a geometric feature of the block universe. Remember, in the B theory, all of time just is. There is no changing the past because the past is just as real and unchangeable as a distant mountain. A CTC is merely a world line that forms a loop within the block. The traveler on a CTC isn't changing anything. They are simply following a path that connects one part of the block to an earlier part. The bootstrap paradox, where an object has no origin, is no more mysterious than a circle having no beginning. It's just a particular shape. This view dovetails perfectly with the Novikov self-consistency principle. The universe demands consistency because the entire timeline is a single, fixed structure. Any apparent paradox is simply a sign that we have misread the geometry. In the block universe, closed time-like curves are not only possible, they are philosophically elegant, reinforcing the idea of a deterministic cosmos where everything is preordained. This brings us to the ultimate human question buried within these theories: fate versus free will. If the B theory and CTCs are correct, what does that say about our choices? The block universe suggests a form of determinism often called eternalism. If the future already exists, then every decision you will ever make is already recorded in the cosmic ledger. Your life is a story that has already been written from beginning to end. This can feel deeply unsettling, as if our sense of agency is a complete lie. We are like actors reading lines from a script, believing our words are improvised even as we speak them exactly as written. The existence of CTCs strengthens this view, showing how the universe's geometry can enforce a destiny where you are compelled to complete a loop, giving the plans to your younger self because that is what always happened. Yet, many philosophers and scientists argue that this is a misunderstanding of what free will could mean in such a universe. Perhaps our choices are not illusions, but are themselves fundamental components of the block. The decision you make at a crossroads is a real event in space-time, and it is the cause of the events that follow on your world line. Your conscious deliberation is the physical process that selects which path you take through the predetermined landscape. In this view, free will is compatible with determinism. It is the experience of being the mechanism by which the timeline unfolds. The feeling of making a choice is real because the choosing is a real physical event. The existence of a CTC wouldn't negate this. It would just mean that the choice to complete the loop was an intrinsic part of your personal, loopy geometry from the start. Ultimately, whether we live in a flowing river of time or a frozen block, the experience of being human with all its uncertainty, hope, and responsibility remains the central mystery that neither physics nor philosophy has yet fully solved. For all their theoretical elegance, closed time-like curves remain a ghost in the machine of general relativity, a mathematical possibility without a single shred of observational proof. So, if we can't build a time machine, how do we actually go about hunting for these cosmic loops? The answer lies not in engineering, but in astronomy, in scanning the heavens for the faint, residual echoes that such profound space-time contortions would inevitably leave behind. The search for evidence is a detective story on a cosmological scale, where scientists look for the universe's own fingerprints, searching for tiny imperfections in the oldest light or subtle ripples in the fabric of space-time that might betray the presence of a loop. One of the most promising hunting grounds is the study of gravitational waves. Since their first direct detection in 2015, these ripples in space-time have opened an entirely new window on the universe, allowing us to hear the collisions of black holes and neutron stars. A gravitational wave is literally a traveling distortion of space-time geometry. Now, imagine the space-time geometry of a closed time-like curve. If such a structure were to form, say, from the rapid interaction of two cosmic strings or within the chaotic interior of a rapidly spinning black hole, its creation or destruction would not be a quiet event. It would send a shock wave through the very fabric of the cosmos, a gravitational wave signature unlike any other. Physicists hypothesize that a CTC-related event might produce waves with bizarre, non-linear features. Unlike the clean chirp of two black holes merging, which rises in frequency and amplitude before fading, a signal from a forming time loop might contain strange echoes or repetitive patterns, a kind of stutter in space-time caused by the causal feedback loop itself. Current observatories like LIGO and Virgo are not yet sensitive enough to detect such exotic signatures, but next-generation instruments like the Planned Laser Interferometer Space Antenna, or LISA, will listen to the universe with far greater precision. By analyzing the subtle harmonics and polarizations of these waves, scientists hope to find anomalies that defy explanation by standard astrophysical events, potential whispers from regions where time itself is tied in a knot. Perhaps an even more profound place to look is the very beginning of everything. The cosmic microwave background radiation is the afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old, a time before the first stars or galaxies had formed. This faint light blanket is remarkably uniform, but it contains tiny millionth of a degree variations in temperature, the seeds that would eventually grow into the vast cosmic web we see today. These imperfections are a fossil record of the universe's most violent infancy. If closed time-like curves are possible, might they have existed in the incredibly dense, energetic conditions of the very early universe? Some cosmological models suggest that in the first fleeting moments after the Big Bang, the entire cosmos was so compressed that quantum gravity effects dominated, and the distinction between past and future may have been blurred. In such a primordial soup, microscopic CTCs could have flickered in and out of existence. If that happened, they would have left an imprint on the cosmic microwave background. The idea is that these causal loops would have subtly altered how density fluctuations propagated in the young universe. The result might be strange, non-random patterns in the temperature map, perhaps circular anomalies or correlations between points in the sky that, according to standard cosmology, should never have been in causal contact with each other. It would be like finding a fingerprint on an ancient relic that doesn't match any known person. Researchers meticulously analyzed the Planck satellite's detailed map of the CMB, searching for exactly these kinds of statistical anomalies. While no definitive evidence has been found, the mere possibility that our universe's oldest photograph might contain a hidden clue about the nature of time is a breathtaking motivation to keep looking. Yet the challenges of this search are monumental and go to the very heart of the scientific method. How do you test an idea that, by its very nature, seems to defy causality? The first major hurdle is the problem of non-falsifiability. A core principle of science is that a good theory must make predictions that can, in principle, be proven wrong. If every observation that seems to contradict the existence of CTCs can be explained away by saying the effect is too small, or hidden behind an event horizon, or requires exotic matter we haven't found, then the idea starts to look less like a scientific hypothesis and more like a mathematical curiosity. Proponents of CTC research argue that they are making concrete, testable predictions like the specific gravitational wave signatures or CMB patterns we just discussed. The challenge is that these predictions are often for effects that are incredibly subtle or require technology we don't yet possess. Furthermore, any potential evidence is almost guaranteed to be ambiguous. If we detect a strange gravitational wave signal, the immediate response from the scientific community will not be, "We've found a time loop." It will be, "What known astrophysical process could have caused this?" Scientists will first exhaust every conceivable explanation within the standard model of physics before leaping to such an extraordinary conclusion. The history of science is filled with anomalies that initially seemed revolutionary but were later explained by more mundane phenomena. This conservative approach is a strength, not a weakness. It ensures that our understanding of the universe is built on a solid foundation of evidence. For a claim as profound as the discovery of a pathway to the past, the burden of proof is astronomically high. The evidence would need to be so clear, so reproducible, and so inexplicable by any other means that it would force a fundamental rewriting of our textbooks. This search, therefore, is a marathon, not a sprint. It requires patience, technological innovation, and a willingness to explore the very edges of what is knowable, all while maintaining a healthy skepticism about the universe's most tantalizing secrets. But our journey through the paradoxes of looping time inevitably leads us to one of the most famous and stubborn puzzles in all of modern physics, a conundrum that has pitted the two great pillars of science, general relativity and quantum mechanics, against each other for decades. This is the black hole information paradox, and it forces us to confront what happens when our current laws of physics are pushed to their absolute breaking point. At first glance, the connection might not be obvious, but the fate of information in a black hole is deeply intertwined with the nature of causality and the potential for closed time-like curves. It all starts with a seemingly simple question. When something falls into a black hole, is the information about that object lost forever? According to Einstein's pure general relativity, the answer is a grim and definitive yes. A black hole is described entirely by just three properties: its mass, its electric charge, and its spin. This is known as the no-hair theorem. Imagine throwing a grand piano, a collection of love letters, and a computer filled with data into a black hole. From the perspective of general relativity, the black hole doesn't care about the difference. It simply gets a little more massive, a little more charged, or spins a bit faster. All the intricate information, the grain of the piano's wood, the words in the letters, the ones and zeros on the hard drive, is seemingly obliterated at the singularity, erased from the universe. This violates a fundamental tenet of quantum mechanics, the principle of unitarity, which states that information can never be truly destroyed. In the quantum world, information is sacred. It can be scrambled, hidden, or made incredibly difficult to read, like shredding a document into a billion pieces, but it must, in principle, be recoverable. The quantum view holds that if you could somehow collect every single shred and have a sufficiently powerful computer, you could reverse the process and reconstruct the original document. The black hole, according to Relativity, appears to be the universe's ultimate incinerator. The paradox sharpened dramatically when Stephen Hawking discovered that black holes aren't even truly black. They emit radiation due to quantum effects near the event horizon. This Hawking radiation is incredibly faint, but it carries energy away from the black hole, causing it to slowly evaporate over astronomical timescales. The critical problem is this: Hawking showed that this radiation is entirely thermal or random. It contains no information about what fell into the black hole. It's like the heat radiating from a warm stove. You can measure its temperature, but you can't tell if the stove is burning coal, wood, or gas. So, if a black hole evaporates completely, disappearing from the universe, what happened to the information about the piano, the letters, and the computer? If the information is truly gone, then quantum mechanics is wrong, and a fundamental law of physics is broken. This is the paradox in its purest form. This is where the connection to closed time-like curves becomes so tantalizing. One potential resolution to the information paradox involves the wild geometry inside a rotating black hole. As we discussed, the Kerr solution allows for a region inside the inner event horizon where closed time-like curves might exist. Some physicists have speculated that the information that falls into the black hole isn't destroyed at the singularity. Instead, it might be caught in these complex causal loops. The information would be endlessly cycled and reprocessed within the black hole's interior, trapped forever in a region of spacetime that is causally disconnected from our external universe. In this scenario, the information isn't lost, it's just locked away in a vault from which nothing can escape, not even information. This would preserve the quantum principle, but at the cost of making the information permanently inaccessible to us, which is a philosophical defeat of its own. A more radical idea suggests that the paradox itself is a glaring sign that our understanding of spacetime is fundamentally incomplete. The point where general relativity predicts a singularity, a place of infinite density where the laws of physics break down, is likely not a real physical phenomenon. It is instead a signal that we need a theory of quantum gravity to describe what truly happens there. In this view, the black hole's core isn't a point of destruction, but a region where the classical concepts of space and time dissolve into a quantum foam. Within this foam, the ordinary rules of causality might not apply. Microscopic closed time-like paths could flicker in and out of existence, allowing for processes that seem impossible in our smooth classical world. Information could be transferred in bizarre, non-local ways, perhaps encoded on the event horizon itself, as suggested by the holographic principle, and then slowly released in the Hawking radiation in an incredibly scrambled form. The paradox arises because we are trying to apply classical ideas of location and causality to a realm that is inherently quantum. The ongoing struggle to solve the information paradox, therefore, is not just an academic exercise. It is a direct assault on the frontier of our knowledge, probing the very same junction where closed time-like curves might reside. Whether the answer lies in information being trapped in causal loops, encoded on a holographic surface, or preserved through some yet unknown quantum gravitational mechanism, the resolution will undoubtedly reshape our understanding of time, causality, and the fabric of reality itself. The black hole is not merely a cosmic vacuum cleaner, it is the universe's most challenging and informative puzzle, a laboratory for testing the laws of physics under the most extreme conditions imaginable. Looking ahead, the quest to understand closed time-like curves is far from over. It is simply shifting to new and more sophisticated frontiers. The next great leap will likely come not from general relativity alone, but from its long-sought union with quantum mechanics in a final theory of quantum gravity. For decades, physicists have been working on two primary candidates, string theory and loop quantum gravity. Each offers a radically different vision of spacetime's fundamental nature, and each could provide the ultimate verdict on whether CTCs are a physical reality or a mathematical mirage. String theory proposes that the fundamental constituents of the universe are not point-like particles but tiny, vibrating strings. The different vibrational modes of these strings give rise to all the particles and forces we observe. In this framework, spacetime is often described as an emergent property, a secondary consequence of these deeper stringy interactions. Some solutions within string theory do allow for closed time-like curves, but a crucial question remains. Are these solutions stable in a full quantum treatment, or will they too be eliminated by effects similar to Hawking's chronology protection? The answer might depend on the specific configuration of the extra dimensions that string theory requires, making the search for stable, self-consistent solutions a major focus of research. Conversely, loop quantum gravity takes a more direct approach, proposing that spacetime itself is not smooth and continuous but composed of discrete, finite loops, a kind of atomic structure of space and time. In this pixelated view of the universe, the very concept of a smooth, continuous path like a closed time-like curve might break down. The extreme curvature needed to create a time loop could be impossible to achieve because spacetime cannot be curved beyond a certain fundamental limit, much like you cannot fold a digital image beyond the resolution of its individual pixels. If this is true, loop quantum gravity would naturally forbid CTCs, not through a protective conjecture, but by the very granularity of reality. The ongoing battle between these theories is not just academic, it is a struggle to define the foundational rules that govern causality itself. While we await a definitive theory, experimentalists are not sitting idle. They are designing ways to probe the fabric of spacetime with unprecedented precision, seeking indirect clues that could hint at the possibility of these exotic structures. Gravitational wave observatories like LIGO and Virgo have ushered in a new era of astronomy, and they are perfect instruments for this hunt. The violent collisions of black holes and neutron stars send ripples through spacetime that encode detailed information about the objects that created them. Physicists are now meticulously searching these signals for any tiny anomaly that doesn't fit the predictions of standard general relativity. For instance, the echo of a gravitational wave could be subtly distorted if it passed through a region of spacetime with unusual causal properties. Or the specific polarization of the waves could reveal hints of exotic matter or energy, the very stuff needed to stabilize a wormhole. Future space-based detectors like the Laser Interferometer Space Antenna, or LISA, will be sensitive to lower-frequency gravitational waves, allowing us to listen to the mergers of supermassive black holes. The environments around these behemoths are where gravity is strongest, and any deviation from Einstein's predictions in these extreme realms could be a sign of new physics, perhaps even the faint signature of a causal loop in the making. On an even smaller scale, particle accelerators like the Large Hadron Collider are also part of the search. By smashing particles together at velocities approaching the speed of light, we create conditions of incredible energy density, if only for a minuscule fraction of a second. In these fleeting moments, the very structure of spacetime might be probed at the Planck scale. While we are nowhere near the energies needed to create a black hole or warp spacetime in a macroscopic way, certain experiments could look for subtle signs of spacetime foam, a quantum fuzziness that might be the hallmark of a discrete spacetime. The discovery of such a granular structure would have profound implications, potentially lending support to theories like loop quantum gravity that naturally limit the formation of CTCs. Other experiments might search for evidence of hypothetical particles like the action, which could be linked to the exotic matter needed for traversable wormholes. The path forward is a combination of immense theoretical creativity and painstaking experimental diligence. It requires building ever more sensitive instruments to listen to the whispers of the cosmos and developing ever more elegant mathematical frameworks to interpret what we hear. The ultimate goal is to move beyond the classic solutions of general relativity and understand the quantum fate of closed time-like curves. Do they represent a genuine pathway through time, a ghost in the mathematical machine that is banished by a complete theory, or something even stranger, a feature that only applies to the quantum world, allowing information to loop back in a way that preserves consistency on a cosmic scale? The answer will not only tell us if time travel is possible, but will fundamentally reshape our understanding of time, causality, and the architecture of reality. While the theoretical possibility of closed time-like curves opens a dizzying portal to the past, the immense physical and logical barriers can feel insurmountable, leaving the dream of witnessing history directly seemingly out of reach. Yet, what if we've been overlooking a form of time travel that is not only possible but is happening around us at this very moment, a method that relies on the most fundamental property of the universe? We don't need to warp spacetime into a knot to observe the past. We simply need to look up at the night sky. Every time we gaze at the stars, we are engaging in a legitimate, profound form of time travel, made possible by a simple, unbreakable cosmic rule, the finite speed of light. Light, while incredibly fast, does not travel instantaneously. It moves through the vacuum of space at a fixed speed of about 1,079,000,000 kilometers per hour. This means that light from any object takes time to reach our eyes. The light from our sun, for instance, is not the sun as it is now, but as it was approximately 8 minutes ago. You are seeing the sun's past. Extend this principle across the vastness of the galaxy. The bright star Sirius, one of our closest stellar neighbors, is about 8.6 light-years away. The photons striking your retina tonight left Sirius around the time a child born today would be entering the 3rd grade. You are seeing a world that is 8 years in its past. Push this further to the iconic Orion Nebula, a stellar nursery roughly 1,300 light-years distant. The light we see today began its journey around the 7th century, at a time when civilizations across the globe were in profound transition. We are not just looking at a beautiful cloud of gas, we are receiving a snapshot from an era that, for us, is ancient history. The most powerful telescopes take this concept to its extreme. When the Hubble Space Telescope peers at a galaxy 10 million light-years away, it captures light that has been traveling through space since long before modern humans even walked the Earth. Every astronomical observation is an act of archaeological excavation, digging into the cosmic past by collecting ancient light. This principle leads to a fascinating, albeit wildly speculative idea. If we could somehow travel faster than light, we could theoretically overtake the light rays that have already left Earth. By positioning a sufficiently powerful telescope an immense distance away and pointing it back at our planet, we could watch historical events unfold as if they were live. Imagine a future civilization constructing a colossal observatory on a planet orbiting a star 1,000 light-years away. If they were to turn their instruments towards Earth, they would not see our present-day cities and satellites. They would witness the light that left our world a millennium ago, potentially observing the events of the 11th century. The key word here is theoretically. This idea crashes headlong into the central tenet of Einstein's special relativity, which states that nothing with mass can reach or exceed the speed of light. The energy required to accelerate even a single proton to light speed is infinite, making this form of travel, and by extension this method of historical observation, physically impossible for any object or information carrying signal. It remains a compelling thought experiment, a poignant reminder that the past is always streaming away from us, encoded in light we can never catch. However, there is a more nuanced and perhaps more plausible alternative that doesn't require breaking the laws of physics. Instead of chasing light, what if we could find a way to gather more of it? The light from historical events doesn't just vanish, it continues to travel outward in an ever-expanding sphere. The problem is that this light becomes incredibly diluted and distorted over interstellar distances. The photons reflecting off a Babylonian marketplace or a Roman legion are still out there, but they are now an impossibly faint, scrambled signal lost in the cosmic background noise. The challenge, then, is not one of speed, but of sensitivity and resolution. A far future technology might involve a telescope of unimaginable scale, perhaps an array of detectors spanning an entire solar system, using the gravity of a star as a giant lens to amplify and focus this ancient light. The concept, known as a gravitational lensing telescope, would require placing detectors at the precise focal point of our own sun's gravitational field, hundreds of times farther away than the orbit of Pluto. The engineering is far beyond our capabilities, but it doesn't violate any known physical laws. Such an instrument could, in principle, resolve the surface of an exoplanet light years away. Applied to the faint light echoes of Earth's own history, the same principle suggests that if we could build a sensitive enough magic mirror, we might one day be able to focus on and decode the scattered light that has been traveling through space for centuries, reconstructing images of the past from the faintest of echoes. This shifts the problem from physics to a monumental feat of information processing. Even if we could collect this ancient light, the signal would be incredibly weak and mixed with light from countless other sources. Piecing together a coherent image from this photon soup would be like trying to reconstruct a specific conversation from the faint roar of a stadium crowd heard from miles away. It would require advanced computational techniques akin to what archaeologists use to reassemble shattered pottery, but on an astronomical scale. Future scientists might employ quantum computers or sophisticated AI algorithms to untangle the signals, searching for statistical patterns and correlations that betray the presence of a coherent image of Earth hidden within the noise. The goal would not be to watch history like a movie, but to extract still images or low-resolution data, enough to confirm major geological events or perhaps the broad patterns of human civilization. This is not the interactive time travel of science fiction. It is a passive, observational archaeology of light, a way to verify our historical records against the ultimate primary source, the universe itself. While it would not allow us to change a single moment, it would fulfill the deepest human yearning to connect with our past, offering a silent, immutable window into the events that shaped our world. And so our journey through the looking glass of spacetime draws to a close. We began with the elegant geometry of Einstein's general relativity, a theory that revealed gravity not as a force, but as the curvature of a unified spacetime. From the gentle warping around our sun to the violent whirlpools surrounding black holes, this single idea opened a doorway to the seemingly impossible. We encountered Gödel's rotating universe, a mathematical proof that time loops were not just fantasy, but a genuine prediction of our most successful theory of gravity. We explored wormholes transformed into time machines through the subtle slowing of clocks, and we grappled with cosmic strings weaving causality into knots. The mathematics is undeniably beautiful, and it suggests a universe far stranger and more wondrous than we ever imagined. Yet, for all the mathematical permission slips, the universe appears to have built-in safeguards. The grandfather paradox presents a logical nightmare, forcing us to consider whether our actions would be constrained by a single, unchangeable timeline, as the Novikov principle suggests, or if we would simply spin off into a new branch of a vast multiverse. More powerfully, Stephen Hawking's chronology protection conjecture argues that quantum physics itself would riot against the creation of a time machine. The vacuum of space, seething with virtual particles, would unleash an infinite feedback loop of energy at the first sign of a causal violation, a cosmic immune system defending the sanctity of cause and effect. The profound challenges of exotic matter and astronomical energy requirements further suggest that if time travel is possible, it is an engineering feat for a civilization so advanced it might as well be godlike. Ultimately, the true value of exploring closed time-like curves lies not in the prospect of building a time machine, but in what the effort reveals about our universe and our place within it. These ideas push the boundaries of human knowledge to the absolute limit, forcing us to confront the deepest questions about reality, free will, and the nature of time itself. They are the ultimate stress test for our physical theories, highlighting the unresolved conflict between general relativity and quantum mechanics, and pointing the way toward a future theory of quantum gravity. By daring to ask if we can loop back to our past, we learn invaluable lessons about how the universe actually works. It is a pursuit driven by pure curiosity, a testament to our insatiable desire to understand the cosmos. So, while a ticket to the past may forever remain out of reach, the journey of asking the question expands our minds in ways that are every bit as transformative. It leaves us with a sense of profound wonder at the intricate and seemingly deliberate laws that govern our existence. The fact that we can even conceive of these possibilities, that our minds can grasp the curvature of spacetime and the paradoxes of causality, is a miracle in itself. Now, we want to hear from you. If you could send one message to your past self, what would it be, and which resolution to the grandfather paradox feels most compelling to you, the self-consistent timeline or the infinite branching multiverse? Share your thoughts in the comments below, and if you enjoyed this journey to the edge of physics, be sure to subscribe for more explorations into the science of the future.